Okay, so here we have the first question that wants to know what the angular speed will be if we convert from 20 centimeters as our radius to 12 centimeters as our radius. We have the mass of the puck, the radius at the start, the radius at the end. And so once we look at the conservation of energy, we see that the masses cancel out, so they're the same for both parts of the equation. And then just squaring the radius for the beginning part and then squaring for the end part, and then solving for angular speed, we end up getting 333.3 RPMs. The question didn't ask it to convert to SI units, so we left them in RPMs. For the second question, it wants to know the tension of in the tendon at a specific angle, at this angle 25 degrees with the tibia, and 40 degrees if the leg is, if you're looking at it, the tendon, determining the angle from the vertical. So I drew out my diagram. Here's the tendon, here's the angle of the tendon to the tibia, and then the angle from the tibia according to the vertical. Attached a fifth of the way down. Here's my center of gravity. The components of each force, we only really care about the y component, and so we set it up for the work done, or not the work, the weight force of y at the midpoint at the center of gravity was the sine of 40 degrees, and then putting in the force at those points. This one was 30, this one was 12.5, so we just solve for that. We get our answer in newtons, 19.28 newtons, 8.03. And then because it's in dynamic or rotational equilibrium, we can just set all of our tension forces to 0. And then it's just plugging and chugging. So we have to solve for tension, which is still what we don't know, at the sine of 25 degrees, a fifth of the way down. And then you're just putting it in, subtract 19.28 because we're going in the negative direction, 8.03. And then, like I said, it's just plugging and chugging. And then we're just solving. At this point, it's just algebra, divide by the sine of the 25 degrees, and we end up with 209.05 newtons. And then for number 3, sorry, I wrote bigger as I got going. So number 3, we have all of our knowns. We're trying to solve for the initial speed of the car, both in miles per hour and meters per second. It's a perfectly inelastic collision. Momentum is conserved, kinetic energy is not conserved. So we're going to solve for the kinetic energy of the car, and then take that and plug it into our kinetic energy equation to find the velocity. Kinetic energy of the car equals the work done by friction to stop the Jeep, the work done by friction to stop the van, the potential energy of the lifted Jeep, and then the work done by friction to stop the car. So we're just going to set that up. We're given the suddenly I'm drawing a blank. I am suddenly forgetting what this is called, but it's to do with friction. It's our constant, our friction constant. Anyway, so we're just setting this up. Friction constant times the mass of the Jeep, etc., gravity, the skid distance. We're going to put all this in, and really then we're just putting in the numbers. The only part that I really had like a little bit of a hiccup on was this part where I accidentally put the coefficient of friction here, but I didn't need it. Anyway, I had to change it. So anyway, we're just going to plug and chug. We end up with the kinetic energy for the car being 32,079.95 joules. And then we just put it in over here, where we have the kinetic energy. This is just algebra. We're going to set it to the other side. The mass of the car, the velocity of the car, which is what we want to know. And then making sure to take the square root. We end up with 6.52 meters per second. And then doing our conversion into miles per hour ended up being 14.59 miles per hour.